Before we close the discussion on using the basic definition of each of the three notations, big O, big omega, and big theta, we need to have the following remarks. First remark, to compare two functions, in particular the running time, and tell which one is larger or grows faster than the other one, we can use the following equivalent notations. First, as an asymptotic notations, we say that f belongs to big O of g, and here we are omitting the input parameter x or n. It is equivalent to saying that f is below g if we have their graphs. Or if we are just comparing functions, we can say that this is also equivalent to f less than or equal to g. Now for big omega, we say that f belongs to big omega of g. It is equivalent to saying f is above g if you have their graphs, which is also equivalent to f is greater than or equal to g as functions. And finally, for f belongs to big theta of g, it is equivalent to saying, if we have their graphs, that f is below and above g. And if these are like functions, then we say that f is equal to g. Now, our next remark, number 2, what does it mean by saying that f does not belong to big O of g? To answer this question, we will solve it by using graphs. So suppose we have a graph one that we have f is below g. So here we say that f belongs to big O of g. Now, when we say that f does not belong to g, so what does it mean? It means that f is not below g, so it should be above g. So we will have the following drawing. And here in this case, we write g is below f, because here we say that f is not below g. So from this graph, we can have two conclusions. The first conclusion, we say that if we look at f down to g, we will say that f belongs to big omega of g. And if we look at from g to f, then we say that g belongs to big O of f. So the conclusion is as follows. F does not belong to big O of g. Then we can have the following conclusion. Either f belongs to big omega of g, or g belongs to big O of f. So what have we done here? If it does not belong to big O, simply remove not from here and change big O into omega. Or just simply remove not and swap these two functions, and this is the result from this notation. In addition to this conclusion, also there is another conclusion. Now, if we have f does not belong to big O of g. Since it does not belong to f of big O of g, then we can say that f also does not belong to big theta of g. Because remember that f belongs to big theta of g if it is belong to big O at the same time big omega. The third remark we have here, we can write it as follows. Now suppose you are given that f belongs to big O of g. So if f belongs to big O of g as functions, it is equivalent to f less than or equal to g. Now this inequality, we will rewrite it, and instead of less than or equal to, we will write it as greater than or equal to. So we will say that this inequality is the same as the inequality g greater than or equal to f. And remember that this definition for big omega. So here we can say that g belongs to big omega of f. So this is the relationship that we have concluded before, is that if you swap between these two functions, then you change big O into big omega, and the statement becomes f and only f. Additionally, consider the following inequalities. And this is going to be remark number 4. Consider the following inequalities. The first inequality will be n less than or equal to 2 to the power n for all n greater than or equal to 1. We will label this inequality as equation number 1. To prove this inequality, use mathematical induction that you have studied in discrete structures 1. So use mathematical induction to prove equation number 1. Now from equation number 1, from this equation, we can conclude that n belongs to big O of 2 to the power n, because this is the basic definition for n belongs to big O of 2 to the power n. Now here, take log of base 2, both sides of equation number 1. So what is the resulted equation? It will be log 2 of n less than or equal to log base 2, 2 to the power n, still n is greater than or equal to 1. Now apply the rule for power inside log, and here we will have log 2n less than or equal to n log 2 of 2, and you know that log 2 of 2 is equal to 1. So the resulted inequality we will have is that log 2 n is less than or equal to n for all n greater than or equal to 1. And from here we can say that log 2 of n belongs to big O of n. This big O relation between log 2 and n can also be reached from the inequality n square less than or equal to 2 to the power n, but n should not start from 1. When n is equal to 1, so what we will get? We will get 1 less than or equal to 2, and it is correct. When n is 2, so we will have 4 less than or equal to 4, also it is correct. But when n is equal to 3, so 3 square is 9, less than 2 to the power 3, which is 8. So 9 is not less than 8, so if n is equal to 3, it's not correct. Now when we try n equal to 4, we will have 4 square, which is 16, and 2 to the power 4 is 16, so it is correct. And when you try 5, 6, and 7, this inequality will be always true, so we say that n should start from 4. Now take log 2 both sides, so we will have log of 2 n square less than or equal to log 2 of 2 to the power n. Now apply the logarithm properties, so you will have 2 log 2 of n less than or equal to. Now when you apply the logarithm rule on power, so n will come down, and the resulted logarithm will be n log 2 of 2, and log 2 of 2 is equal to 1. So here we will have less than or equal to n for all n greater than or equal to 4. Now divide this equation or inequality both sides by 2. So what we will get? We will get log 2n less than or equal to half n for all n greater than or equal to 4, and this implies that log 2 of n belongs to big O of n, which is the same result that we have obtained from the previous inequality. Now for the next inequality, it is 2 to the power n less than or equal to n factorial, and n should start from 4. We will label this inequality by 2. Now to prove this inequality, you can use mathematical induction. So here we write use mathematical induction to prove equation number 2. So now we can say from equation number 2, we can conclude that 2 to the power n belongs to big O of n factorial. Why? Because this inequality represents the basic definition for big O. The value of g of x is n factorial, the value of c is 1, and the value of k is equal to 4. We will also now start from the same inequality. We will say 2 to the power n is less than or equal to n factorial. Now we will replace n factorial by its definition, which is defined as n multiplied by n minus 1 multiplied by n minus 2, and it goes all the way multiplied by 2 and then multiplied by 1. Now if I replace n minus 1 by n and I replace n minus 2 by n, all the way 2 by n and 1 by n. And you know that n is greater than n minus 1, n is greater than n minus 2. So this factorial will not be equal to this factorial when every other term than n is replaced by n. In fact, this will be larger. So we can say that 2 to the power n is less than or equal to n multiplied by n multiplied by n, and this n is multiplied n times, and as a result we will have 2 to the power n, and finally we will say that 2n is less than or equal to n raised to power n. Now take log base 2 for both sides of this inequality. So take log 2 both sides. So what you will get? You will get log of 2 to the power n less than or equal to log of 2 n raised to power n. But this time n should start from 2. Why? Because the original inequality n starts from 4, and if you take log 2 of 4, you will get 2. So this is why n should start from 2. Let's continue the solution. Apply the properties of log. So we will have n log 2 of 2 less than or equal to n log 2 of n. And this is equal to 1. So at the end, we will have n less than or equal to n log 2 and n greater than or equal to 2. This represents the basic definition between n and log 2. So we can conclude that n belongs to big O of n log 2 of n.